Thank you. So yeah, um, my name is Eric Roon. I'm a first-year postdoc at Michigan State University. I'm here to talk to you about some recent work on finitely correlated states driven by topological dynamics. And you might see here that I tried to come up with a snappy acronym for the talk, but Words with Friends wouldn't let me play Qfitoa. Turns out that's not a word. So I should mention that this is based on some work that I did with Brent Nelson a couple years ago and new work with Jeff Schenker that's dropped on the archive today. So I just want to fix some notation first. So we've all seen these quasi-local algebras all week. And I guess I kind of conform to Bruno's convention. So we'll take the on-site algebra to be n by n matrices, and then you conform the quasi-local algebra in the usual way by tensoring with all of these sites inside of lambda. I'm going to be focused on the quantum spin chain, so you can take these to be intervals, and then you can close it up with respect to the operator norm. And like Emil was teaching us the other day, there's a canonical group action on the lattice by self-action. And so there's this extends to a group action on the quasi-local algebra by basically changing the address of the pure tensors. So here, AX is some matrix and AX plus K is that same matrix, but now we think of it as having moved to the site X plus K. And you can show that each one of these tau Ks extends to star automorphism, and they're a group action. So whenever you have some sort of symmetry in physics, the sort of modus operandi is to think about things that don't care about it. And so we'll recall the state as translation invariant if I can compose with all of these translation automorphisms and get the same state back. So this is sort of agnostic about the address of the local observables. And one thing that I want to mention, which is a bit of a verbal quirk of mine, is that I use the word quantum channel to mean a unital completely positive map. I work in the Heisenberg picture for the most part, so this is the natural definition of quantum channel for me. But I also wrote a paper with somebody who does type 3 von Neumann algebras who insisted that this is the terminology we use. So I want to talk about some motivation. So back in 1992, this paper by Finitely and Werner on finitely correlated states came out. And one of the many things that they prove in this paper is that the following are equivalent. So if you have a translation invariant state on the spin chain, then you can show that there exists an auxiliary unital C-star algebra B, some quantum channel that couples the one-site algebra to this ancilla and sends it back. And a state in the dual of the ancilla, so that when you look at the expectation value of some pure tensor observable, this is actually witnessed as linear dynamics on the ancilla, where we've sort of abbreviated here E sub A as a stand-in for the curly E with A in the left tensor factor. This picture just sort of keeps the notation a little bit cleaner. So these have come to be known as transfer operators in the succeeding 3 decades, and I want to point out that, in fact, Finitely-Werner proves something much finer. They give exact conditions so that B can be considered as a finite dimensional operator system. If you don't know what that is, that's okay. It's basically like a subspace of a C-star algebra that contains the unit. So it's not quite a C-star algebra, but it's just as good. And so the motivation for my group is, oh, sorry, I was ahead of myself. So an important application of all of this formalism is the AKLT model, which Bruno introduced to us earlier last week, which is that if you take the spin 1 chain, you can find some AKLT ground state that is the unique ground state of some nearest neighbor local Hamiltonian. And one way that of expressing this state that was pioneered in this paper is now known as the matrix product state representation. So I'm just going to flash the formulas up here, but if you sort of let gamma n be sums over these spin z configurations in some interval, you can take the trace of products of matrices which are labeled by the symbols and put them against the computational basis. And one of the things that Finitely-Werner prove is that if you look at the vector state associated to this thing, that converges to the AKLT state in the weak star topology as you take the thermodynamic limit. And these matrices don't just come out of nowhere. They're actually embedded inside of this transfer operator framework because you have a partial isometry from this sort of singlet doublet coupling where these are the block matrices.
just wonder, in the previous theorem you stated, can we say that any 1D gap state have a matrix product representation? Because of the way you put it, that looks like, but whether that's equivalent?
No, that's not quite what the last theorem is saying. It's saying that if you have a translation invariant state, then you can find some C-star algebra that describes its translation via these linear dynamics. Yeah, so I'm making no claim about gapped or gaplessness here.
If the translations have a gap, you get the matrix product representation?
Well, not quite, because there's no guarantee that this is finite dimensional. In general, you take this just to be the right-hand side of the spin chain. Yeah. Okay. So my group is focused on modeling disorder. And so we want to introduce some on-site disorder into this transfer operator framework and kind of see what pops out. We're mathematicians, so we can do that. Why not? And for our purposes, the purposes of this talk, we're going to do this by fixing some compact Hausdorff space omega and some homeomorphism from omega to omega that forms a topological dynamical system. This seems at first for any analysts in the room that this is like a really restrictive condition, but actually there's a theorem called the Jewett-Krieger theorem that says that basically any ergodic system on like 0, 1 with Lebesgue measure can be viewed in this way. And so what's the core idea? Well, we want to replace these transfer operators with some random transfer operators that depend on the disorder parameter, but every time you translate, you want to twist by your ergodic operator a little bit. Or sorry, your homeomorphism a little bit. In the probability setting, this is viewed as an ergodic map. So what kind of thing results from doing this? Well, for finite dimensional on-site algebras and for the case when the on-site algebra is a tracial von Neumann algebra, we have the answer. Namely, if we have this family of random transfer operators, one notices that this means that E sub 1 is a random quantum channel. And if you suppose with sufficient positive probability that the stochastic process associated to doing these compositions with this twist converges to some limit, then you can actually just kind of shove this disorder framework into the existing transfer operator framework and you get a state. And the state has some interesting symmetry. Namely, if I compose with a translation automorphism, I get a twist in my dynamical system on the disorder space. So it's no longer translation invariant, but it's statistically translation invariant. If I took an expectation in the disorder, if I took the mean, then it would look like a translation invariant state. So we call this thing the translation covariance property. And note that I needed to point out tau k is translation by k sites. And notice that we have to point out that this quantum channel has some convergence property because we need this equation here to be consistent with the embeddings into larger volumes. Okay. So did we describe all of these things? So both of these works by Ramis Mavasa and Jeff Schenker and Brent Nelson and myself show that you can do this random transfer operator thing and you get these translation covariant states. But what about the other way? We had to suppose that these transfer operators sort of fell out of the sky, and in Finitely-Correlated, they give an equivalence by constructing the ancilla and showing what these operators actually are. So we also don't have some explicit examples that have like a really good kind of interesting properties. And so this is something that motivated Jeff and I to take a closer look at this. And so let me tell you about what we did in our new paper. So I'm going to lead with a procedure to kind of try to construct this ancillary object, and I'm going to draw a bunch of pictures. So this is inspired by what was done in Finitely-Correlated, and just fun fact, it was actually 366 days ago that I pitched this idea to Jeff, so not the only anniversary that's going on. And so what's the thing that we're going to do? We're going to cut the spin chain at the site -1/2 into left and right-hand sides. And then we know that there's some operators on the left and some operators on the right that act as observables. And the way that the state views them can be thought of as just taking the tensor product and evaluating. But it's possible that there's maybe some other observable over here that gives us the same expectation values with respect to a fixed C as A does. And so there's some, I guess you can think, degeneracy there, and we want to exclude that possibility. So we just want to figure out exactly what type of correlation the state is seeing across the cut. So you can define an equivalence relation, tilde sub omega, where A and B are equivalent in the right-hand side if for every C on the left, their difference evaluates to 0. So this is roughly saying that if I take A minus B, then the state will factor over these two things. So notice that here I have inserted this little omega, which is living in my compact Hausdorff space, but there's no reason that I couldn't have chosen a different one. And so the resulting object, by the way, I want to say, is some equivalence class that's labeled by this point. So let's see what happens when we choose a different one. Well, we get the same thing, except now it's labeled by a different point. And in fact, if you look at the quotient space of this right-hand side via this equivalence relation, you get some Banach space, which is also labeled by these base points. So you can see that if I switch between omega and omega prime, there's not really that much difference between them. And so somehow these things should be kind of similar or at least tied together in some way. So here's a picture of what I'm talking about. Here's our fancy potato omega, and you can do this construction for each point in here. And as a probabilist, what I see when I see this a comma omega thing is that this looks a lot like a random variable. But random variables need some sort of measurability structure, and it's not immediately clear what to do for that structure here. So in order to talk about random variables in this sense, we need a continuity structure. So this is the first theorem that we proved, and namely, it says the following. So if each one of these B omegas is finite dimensional, then they can be uniquely topologized into something called a Banach bundle that makes every function from omega into one of these equivalence classes a continuous section of the canonical projection. And in particular, you can actually find bundle homomorphisms from B into the trivial bundle, some section into B, and covariant homomorphisms labeled by things in the on-site algebra so that this factorization holds. So we've achieved actually some kind of version of a converse to the previous theorem that we had. So this one plays a special role, and so it gets a special name, namely it's called the small correlations bundle. So we're still lacking a little bit of an equivalence because we want to try and push this as hard as we can. So let me show you the sort of more technical statement, which is the following, due to me and Jeff. So if you have a weakly star continuous mapping into the state space with translation covariance, then the following are equivalent. Namely, it's finitely correlated. So these tensor factors fixed by objects on the left look finite dimensional in the dual. And you can find some Banach bundle with finite dimensional non-trivial fibers and a triple of homomorphisms and sections so that this factorization holds. Moreover, the small correlations bundle is minimal with respect to certain spanning conditions. And so if you find one that, if you find a C that does this, somewhere sitting inside there is the minimal bundle. Okay, so I told you a goal that I had, and we've walked sort of through the proof, and we achieved the goal, more or less, with some restrictions. So where do we go from here? Well, we want to assess how big of a class of states these small correlated states are. In Finitely Werner, they characterize the set of translation invariant states and the set of finitely correlated states as convex subsets in the dual space. And then they also show that the finitely correlated states are weak star dense. So it's not hard to show that these translation covariant guys and the small correlations guys are convex sets. One lives inside the other. So what about density? It turns out that we do have weak star density. Namely, if you start with a translation covariant state, for any epsilon, you can find some psi omega with this small correlations bundle, so finite dimensional fibers, so that uniformly in this continuous disorder, I get an estimate that looks like this. Namely, this is sort of a uniform in disorder parameter density type of theorem. Okay. Okay, so At this point, Jeff and I were like, okay, great. So we're on track to like fully generalize this paper. And then Jeff asked me, well, what about an example? And we were stumped for a couple of months thinking of trying different things to modify known examples and get this disorder to pop out in the right way. And then one day we noticed that the AKLT model actually lives inside of a parameterized family of matrix product state models. And ask the simple question, well, what if we made that parameter disordered? So I'll give you another procedure. So what we're going to do is pick a family of IID random variables, which take values in 0 to pi over 2, or pi over 4, sorry. And that's a restriction for technical reasons. And then this sentence here is just saying that I want these things to look as if they're distributed by a continuous function. Then these are the general formulas for this parameterized family of the AKLT model. And what you can do is basically shove this into the transfer operator framework that already exists for the AKLT model, except what you do is at each site you interrupt the parameter by making a different IID choice. And so this actually shows that this is finitely correlated in the sense that we had before, because you are sort of passing through the trivial bundle of 2x2 matrices times your disordered space. And moreover, you can easily check that this E1 guy is a unidal trace-preserving quantum channel. So we have the consistency conditions required so that this can extend to a state in the thermodynamic limit. So let's talk about some properties of this thing. It's finitely correlated. We just saw that. Furthermore, there is a random nearest neighbor parent Hamiltonian for which this is the unique frustration-free ground state, and that holds almost surely. But also something interesting happens, namely for any length scale, with probability 1, I can find somewhere on my spin chain that depends on the disorder so that a lower bound of the following form happens. So here I've got the spin Z matrix, and I have its translate. And when I plug these into my new omega, I get a lower bound in terms of cosine with this interesting decreasing parameter here. What this actually means is that with probability 1, the bulk gap of the GNS Hamiltonian has to close. This is maybe not surprising because if you, in general, just take a random Hamiltonian, it's probably unlikely that you'll get a gap. But what's interesting is that the spectrum of this thing is actually constant in the disorder. So that's kind of fun. But on the other hand, if you pick some small number in between 0 and 1, and you have a specified interval, then you can find some random constant so that the correlations of this thing are actually exponentially decaying almost surely. So how do we square these two things where this lower bound is happening and this exponential decay is also happening? Well, it's because of this constant. So this is a random constant, which is finite almost surely, but we don't have any restrictions on where it lives. So on one of these sort of long patches where you're close to 0, this constant can kick your correlations up, basically. Okay. So we have a structure theory. We have an interesting example. And it seems like I've sort of taken a very large departure from the theme of this conference because we're talking about something disordered. And then it was suggested to us by a friend that we should take a look at some index calculations. So it's not hard to show that for all values of omega in range, this thing has time reversal symmetry. In fact, you just take the matrices that you already have and notice that time reversal is implemented by some 2x2 unitary, and then you just plug it in and that's that. Previous work by Tasaki has shown that in the deterministic case, there's a Z2 index associated to deterministic MPS with this translation symmetry, or with this time reversal symmetry. And furthermore, you can calculate this thing as a string order parameter. So what does that mean? It means that there's a family of operators, namely these Lieb-Tasaki operators, which are tensor products of unitaries. And then as you send L to infinity, the expectation value of your state should converge to 1 or -1. And this is enough to distinguish deterministic AKLT from the deterministic trivial state. So what happens in our case? Well, in L1 norm, we show that this string order parameter converges to -1. So it's not quite almost sure convergence, but it's something interesting. That's all I have to say. Thank you very much.